So here's this very same, and it's meant to be the same. So let me show you that I'm just trying to sort of extend this page from before. So this is the dashed line that represents the center of mass, or you could say it's the center of collision in a way. Yeah, so this is I'm going to explore the issue of the center of mass when I explore, or maybe right after I explore the conservation of momentum in the videos. So, but nonetheless, this is the center of mass location. And let me just replay the incoming stuff. Masses 1 and 2 on a collision course. Okay, so here comes number 2. And we had it moving kind of slow compared to number 1 that was moving faster. And let's play out some of the other types of things that could happen. So here's one. Number 2 leaves the collision zone, so with a little bit of damage. So let me put that number 2 has been crushed a little bit, and it's moving away kind of slow. And number 1 is also moving away kind of slow and is also damaged. So I might say there is damage, right? Both number 1 and number 2 are damaged. They both leave. Number 2 is moving away slow, and number 1 is moving away slow as well. But number 1 is moving away, in particular, it's slower than what it came in with. So we may say that if this was V initial for number 1, and this is V final, for number 1, we'd say that V initial for number 1 has a magnitude. So we're just talking about the speed that's bigger than V final for number 1. So we'd say that what has happened is there's been speed loss. And then number 2, same kind of idea. V initial for number 2 has a magnitude that's going to be bigger than V final for number 2. This is the idea. So there is speed loss. I don't like this very much because it doesn't really tell you any physics, but this is what is sort of similar to the idea of some kinetic energy is left, but not as much as pre-collision. Can you see that if both of these two objects leave the collision with smaller speeds, then another way to view this is they leave the collision with not as much kinetic energy. From the conservation of mechanical energy, what this would say was there must have been work done by dissipative or dissipation style forces like friction. In fact, actually, there is some really interesting work done that's associated with the missing kinetic energy. And this work was the forces involved in crushing the object. And can you see that the crush, it's permanent? We would say it's got a permanently damaged. So this is the dissipative work. So yeah, this is where we lose the kinetic energy. We lose mechanical energy in that collision. So this here is an in-between case of perfect elastic and perfect inelastic. there is somewhat of a loss of kinetic energy, but there is kinetic energy left. So the last type of collision that I'd like to show you is, actually I might show you two more because I've got time in this video. So the next one is, I'm gonna name it first. So the name of this style of collision is referred to as super elastic. So in a super elastic collision, what happens is in the previous video, I kind of described that maybe number one and number two, when they collide, there's an explosion that goes off that makes them separate very, very fast. So after the collision, they both leave the center of mass position extremely fast. So here's number two. It's moving away very, very fast. So its final velocity is represented, it is more speed than its initial velocity, and number one is the same. So here goes number one, a whole bunch of speed, way faster actually than number two, because remember it was kind of the faster object. So V final for number one is way bigger than V initial for number one when you talk about speeds. So in this super elastic case, there is more kinetic energy after this really interesting collision process. Yeah, so there's more kinetic energy. So this is referred to as a super elastic collision. And then I'm gonna just one more type of collision, and the truth is this is honestly where stuff becomes more realistic. Yeah, especially when you talk about things like cars, for example, or yeah, imagine a nail hitting a magnet or something like that. Yeah. Okay. So let me just. This is just for funny stuff. So funny, crazy. Anything goes. Kind of a theme. So here's number two, but it's only half of number two. So here is the back half of the two, and it's headed this way. And here is the other half of two, actually, and it's headed away kind of quick. And here is the other half of two. So this is the half that's the piece of two that goes that way, and it's actually stuck to number one, and it's headed away somewhat slower. And in this case, I'm not sure about kinetic energy. It could be anything. It could have been that number two exploded into two halves. So here comes number one and number two. The left-hand side of number two gets stuck to number one, but inside of number two is actually a spring-loaded separator. So number two pops in half. And so when it pops in half, the left half of number two and number one run away, and then the right-hand side of number two runs away this way. Yeah, it could be like that, or some funny, crazy, anything goes kind of a thing. I don't know, if you come up with an interesting collision, you can name it yourself. It doesn't really matter what its name is, but it is possible, right? Like, you could imagine that this is something that could happen. But the point is this is a situation that has a mass exchange. So it's kind of like I make a new object, it's 1 plus half of 2, and the other object that's left over is the other half of 2. So there is this mass exchange that can happen. Yeah, lots of other things. So sky's the limit, right?